Hi everyone. In this section we're going to be working on 3 topics: telescoping series, geometric series, divergence test. Whenever you're working with telescoping series, it's usually whenever you're adding or subtracting 2 fractions. Whenever you have a geometric series, it's usually whenever n is in the exponent. And the most important theorem that kind of helps you out is divergence test. Because if ever you take the limit as n approaches infinity of your series, and it doesn't give you if it doesn't give you 0, then the series is going to diverge. So we're going to work on all 3 of these throughout this video, and then hopefully it can help you out. So the first things first is in 9.2, whenever you're working with series and if they converge, you have to go back to 9.1. 9.1 was all about sequences, infinite sequence. The difference between the sequence and the series is the fact that in a sequence, all you're doing is you're listing all your terms. Your first term, your second term, your third term, and whatever your last term is. But in the series, in this section, and for the rest of this chapter, what you're doing is you're taking all of your terms, but now you're actually adding them together. So it'll be like A1 plus A2 plus A3 plus any other term all the way to your last term. So once you understand the difference between a sequence and a series, then it can kind of help you to figure out if it's going to converge or diverge, kind of like what you did in section 9.1. So what we're going to do is we're going to first work on that first type of series, which is a telescoping series. Now, telescoping series behaves in patterns. What you're going to realize is you're never going to actually understand what you're working with until you see a pattern. Remember how in the beginning I told you whenever you're adding and subtracting 2 or more fractions, you're probably working with telescoping? Well, that's what this case is. 2 fractions are being added and subtracted, so let's just go ahead and figure out what these terms are going to be. Now in this section, you also learn something called partial sums when you're trying to list the sums of all the terms. So let's just go ahead and find the first term. Well, if I found the first term, my first term is me taking 1 and plugging into this n and this n. So that what that's going to give me is 1 over 2 times 1 plus 3. So that's going to be 1 over 5. Plug in the 1 here, 2 times 2 plus 1. And you're going to get 1/3. But that's not really going to help me out. What I need to do is I need to find the second term. Same thing. Take 2, plug it in there. You're going to get 1/7 minus 1/5. Now, you're going to realize something. You see how this term is the same exact thing as this term except it's opposite? Meaning it's going to cancel out? That's probably a pattern. So what we're going to do is we're just going to go ahead and find the third term to see if this pattern continues. Well, if I take this 3 and plug it into both of these, I'm going to get 1/9 minus 1/7. What that means is this first term is canceling out with this last term of the second term. Well, and that means that this term is also canceling out with this one. That's a pattern. What that means is I'm trying to find a partial sum. So I'm trying to figure out what's remaining, what is not canceling out. Because as of right now, this first term is canceling out with this term. First with the second of the next one. First with the second of the next one. So then you have to ask yourself, okay, well, what about the last term? Something's going to be remaining. Well, the last term is going to be your n equals, well, let's just say n term. What is your n term? Your n term is exactly what this is. I'm going to plug in n into there, and it's the same exact equation. 1 over 2n plus 3 minus 1 over 2n plus 1. Now remember, what we're trying to do is we're trying to find out all the sums of every single term all the way to infinity, because it starts at 1, it goes all the way to infinity. All the way to infinity, which this would be your last term. So everything will literally cancel out. You see how this is all canceling out? Now, a general rule is whenever you notice that this is going to cancel out, this right here, everything cancels out, you can kind of look at the first term and your last term and ask yourself what's remaining. You see how this is remaining and this is remaining? Pretend this term was this term, meaning that what's going to be remaining is this as well as this. And the reason why this is going to cancel out is because if this took the place of that, this term would cancel out with the last one, which means that this term would cancel out with this term. So that's why it's a little important sometimes to see what's happening, but things are going to cancel out. So what my equation is going to be is my partial sum is going to be S of n is equal to what's remaining, which is negative 1/3, plus this term, 1 over 2n plus 3. Now with partial sums, all you have to do, your next step, is literally just find the limit as n approaches infinity of negative 1/3 plus 1 over 2n plus 3. And just using basic limit properties, this is just going to be negative 1/3. This is going to end up giving you 0. So then your final answer, your sum of this telescoping series, is going to be negative 1/3. So once again, how do you know things are telescoping? Whenever you notice that you're adding 2 or 3 fractions or subtracting. And then once that happens, once you notice that pattern, plug in the first term, plug in the second term, usually plug in the third term. If you notice that this all cancels out, just go ahead and put your last term. And then pretend that this term is this term. And then whatever's remaining is going to be what's left of your partial sum. It's a little confusing at first, but it takes practice. So what we're going to do is we're going to work on the next one. Now, in our next term, once again, same exact thing. You're going to be given a random example and you have no idea what you're working with. Well, the fact that there's 2 fractions being added or subtracted to each other probably means we're working with telescoping series. So then what we're going to do is we're going to go ahead and find our first term. Now, if we go ahead and find our first term, remember, our first term is the first term is actually n equals 0. So what we're going to do is we're going to plug in 0 into here. And when we plug in 0, that's going to be, actually no, let's not even do 0, let's do 1, because that's not even going to work out. So when n is equal to 1, plug in 1, you're going to get 1 minus, plug in 1 there, 1/3. That's not really going to help me out, so I need to figure out what my next term is, which is n is equal to 2. Plug in that is going to be 1/2 minus 1/4. As of right now, you have no pattern. Nothing is canceling out. So because of that, chances are you're probably going to need a third and a fourth term. So I'm going to plug in n equals 3. And that's going to be 1 over 3 minus 1 over 5. Now finally, I get something to be telescoping. This negative 1/3 is going to cancel out with this term. But nothing cancels out in the second term, which means I'm going to have to figure out my fourth term. Usually you never go past 4 terms. The only time you ever do is when you notice that your second term isn't canceling out. So then I'm going to go ahead and do that. And I'm going to plug in 4. That's going to be 1/4 minus 1/6. And you'll realize finally this 1/4 is canceling out with this 1/4. So then you have to ask yourself, okay, well, what's remaining? Now the problem with this is the fact that the second term didn't cancel out means that I need 2 terms at the end. Remember, this goes from 1 all the way to infinity. So we got to figure out what is not going to cancel out towards the end. Well, the ones that aren't going to cancel out, pretend these were the last 2 terms. Is the second one of the last term and the one before of the second one. So we're going to do, okay, well, let's figure out our last term. Well, we all know, remember, same as last one, our last term is n is equal to n. So I'm going to plug in this n into that, which is the same exact equation. So it's literally you're copying it down. Then you have to figure out, okay, well, what is your next to last term, which is your n minus 1, because if n is your last term, then 1 less than that would be the second to last one. You're taking n minus 1 and you're plugging it into every single n. So if I plug in n minus 1 into that n, hopefully you guys agree it's going to be 1 over n minus 1. Well, then when I plug in n minus 1 to this n, it will be like n minus 1 plus 2. So if you combine like terms, hopefully you stay with me, n minus 1 plus 2 would just be n plus 1. And that would be my second to last term. But remember, stay with the pattern that you're taking this term and literally replacing with that. So ask yourself, what canceled out? You see how this one canceled out and this one canceled out? That means this is going to cancel out and this is going to cancel out. So you see how this was remaining, this is remaining, these 2 are remaining. But at the end of the day, this is going to cancel out because the pattern is going to repeat. All we're doing is we're using these to kind of mimic our last 2 terms. And then our partial sum, what we're remaining, is S of n is equal to that 1 because it's never going to cancel out, this 1/2 because it's never going to cancel out. Reason why we had to do the last 2 terms, as well as this minus 1 over n plus 1, as well as this minus 1 over n plus 2. And then lastly, find the limit as n approaches infinity of S of n, which is literally all of that, and just think of all the limits properties I can't. That limit is just going to be 1. This limit is just going to be 1/2. This is going to be 0 and 0 by L'Hopital's rule, or you can do your HA rule. And then when you add these two together, you're going to get 3/2, which means that the sum of this equation is 3/2. And also remember, if it actually adds up to give you a number, that means it converges. Okay? Now, this one, in respect to the one we just did, is very complicated. It only happens when you notice that your second term is not going to cancel out. When your second term is not going to cancel out, find 4 terms and then mimic the last 2 terms with the last of the last 2 terms. And literally mimic it, and whatever's remaining, you write it as your partial sum, then find your limit. Now, the one thing about telescoping series is the fact that you're able to actually see what the sum is going to be. Majority of the series that you're working with, you're not going to be able to figure out the sum. Okay? So the first one's telescoping, that you can find the sum, and it's going to converge to 3/2 for this problem. And the next type of series that we're going to be working with that we can find the sum, if it converges, is geometric. So in a geometric series, changing pace a little bit, geometric series has a pattern. You're always going to know what is geometric, and that's usually because that n is in your exponent. And these are the 2 examples that you're going to see. Our first example is when n is equal to 0, and it goes to infinity of your summation. Then your exponent is going to just be n. And this a stands for the first term. Remember, a stands for the first term, r stands for the ratio that's being multiplied constantly. And then n is just whichever term that you're working with. Or you can find it in the series that's n equals 1 to infinity, and then you'll realize that your exponent is n minus 1. The most important rule about geometric series, this number has to match up with that. So if this was like n equals 2, that has to be n minus 2. If this was n equals 4, that has to be n minus 4. Very important to understand that. We're going to work on a problem where they're different, and you'll see how we actually figure it out. Now, when the absolute value of r, your ratio, is less than 1, that means your series is going to converge. Which, remember, if it converges, that means that we're going to be able to find the sum. And to figure out the sum, it's a over 1 minus r, where a is your first term and r is whatever your ratio is. But in the case where the absolute value of r is greater than 1, our series is going to diverge. And the reason is, technically, think of it as if r was like, I don't know, 3/2, or just, let's say, 4, just the number 4. Whenever you raise 4 to a power, that number is going to get really, really big, which means if we had to find that sum is going to be so huge as it goes to infinity that we don't really know where it's at. So that's the reason why it diverges. But in the case of geometric series, if our series happens to converge, we can find the sum by this formula right here. And it's only when our r is less than 1, and it has to fit these 2 patterns. So we're just going to go ahead and look at an example. Example 1 of geometric series. The summation from n equals 1 to infinity of 3, which, remember, 3 is your first term, as long as this number matches up with that number, which it does. Our r is negative 1/2, and our power is n minus 1. So since that matches up that, I don't have to do any work. Now my only thing is, okay, well, let's figure out what a sub 1 is, which is that number right there, which is 3, and figure out what r is. R is equal to negative 1/2. Well, because r is equal to negative 1/2, take the absolute value of that, and you see how it's less than 1? So that means that our series is going to converge, which is nice because now we just have to actually figure out what our sum is going to be. And our sum is only going to be 3 over 1 minus negative 1/2, which is 3 over 1 plus 1/2. Combine like terms. 1 1/2 is 3/2. Keep, change, flip. And this is going to cancel out, which means that your sum is going to equal to 2, and that's your final answer for this geometric series. So geometric series are nice to work with when in the perfect form, because literally you just have to follow the fact that if your ratio is less than 1, the absolute value, it's going to converge, plug all the numbers into here, and find what the sum is, and if it's greater than 1, it's going to diverge. So as of right now, the only series that we can figure out if they're going to have a sum is telescoping and geometric. So now we're going to work on our next example. In our next example, you'll realize something's just randomly given to you, and you're going to go, okay, what do I use? I notice there's fractions, so could it be telescoping? But also remember this, you see how that your exponent happens to be n? Whenever your exponent is n, chances are you're working with geometric series. Now, with summations, you're able to split them up. So you could actually take this and split it up so that you're working with two different summations opposed to just working with one fraction. Now, if you take a look at this one and then you take a look at this one, these are two different geometric series, but you have to make it a little bit nicer. It's not really in the form of a1 and then your r to the n power. So then what I'm going to do is I'm just going to rewrite this as n goes to infinity, n goes to 0 to infinity of 1 over 2 raised to the n minus the summation from n equals 0 to infinity of 1 over 3 to the n. Then your next thing is, okay, well, what is your first term? Well, you see how this 0 matches up with that because there's no number being there? That means your a is that number right there, which would be a equals to 1 and your r is equal to half. And in this case, same thing, it matches up, so that means a is going to equal to 1 and r is going to equal to 1/3. Well, let's just go ahead and find the sum. Well, since 1/2 and 1/3 is less than 1, that means the series is going to converge, which is nice because now we can actually go ahead and find the sum. So that means that we're going to do a, which is 1 over 1 minus 1/2 for this one, and then this one is going to be 1 over 1 minus 1/3, and then after you find these two sums, you're going to just literally bring down the sign and you're going to subtract these two sums. So when you combine these, this is going to be, you know, LCD, etc. 1 over 1/2 minus 1 over 2/3. And then when you keep change flip, this is going to give you 2 minus keep change flip it, it's going to be 3/2. Once again, find your LCD. 4. This is going to end up giving you 1/2 as your final answer. So that means that this summation is going to converge to 1/2. So sometimes you're able to break it apart to make it a little bit nicer. Okay? And then your last problem for geometric series is what happens when your exponent, when you realize it's a geometric series but your exponents don't match up. Remember the form we said, if this is 1, these exponents have to be n minus 1. They just have to be n minus 1. So you're going to go, okay, well, what can I do to make this n minus 1? The fact that that doesn't say n minus 1, I have to get rid of this plus 1. I don't need it. So the first step, whenever you have that, is break it apart. Make this e to the n times e to the 1, which still makes sense because remember, when you have the same basis and you're multiplying, you add the exponents. So this is just simply just me restating this as that. But remember, you need n minus 1. You need a minus 1, so you have to include that. So then, one thing about algebra is I can include whatever I want. I can include an e to the negative 1, but as long as I include an e to the first. Because remember, if this e to the first and this e to the negative 1 were to be combined, it cancels out, which leaves me with the stuff here. But remember, I need an n minus 1 as well on top. So then I'm going to add a negative 2 to the negative 1 because this is going to give me what I want, but I also have to cancel out, so I have to add a negative 2 to the positive 1 because these will cancel out, which just still leaves me the stuff in black. Now I'm going to rework things. And this is where it gets a little confusing. These two get combined to give me, and I'm going to put it over here, negative 2 to the n minus 1, because remember, when you combine like terms, you add the exponents, so it'll just be n minus 1. But then I have this on the outside. And in the bottom, this and this is going to combine to give me e to the n minus 1, which I want, but then these two are just left hanging by itself, so I have to include that. A to the 1, e to the 1 will just be e to the 2. So now this looks a little better because this 1 now has an n minus 1. So my next step is just to rewrite it. This is just going to be negative 2 over e squared. And then this is going to be negative 2. And what I should do is I should actually split this up to make it times e to the n minus 1, n minus 1. But I still want to rewrite this. So this is going to be negative 2 over e squared times negative 2 over e n minus 1. And then finally, I have it in the form that I can work with. Well, when I plug in 1, 1 minus 1, 0, this is going to cancel out, leaves me my first term. So I know A1 is equal to negative 2 over E squared. And this is going to be my R, which is negative 2 over E. So in this problem, it makes sense because now this 1 is that 1, and it has to match up. So sometimes there is a little bit of work. Whenever there's a number that you don't need, split it up, and then add what you need, but also add so that this cancels out to top and bottom if needed. Now, the next thing is, look at this R. Is this going to converge or is this going to diverge? Now you may think, okay, well, I don't know what E is. Why is there an E? That's throwing me off. Well, remember, E is just 2.71 and etc. Well, 2 over 2.71, that would be less than 1, which means it converges, which is nice because we know it's going to add up to a number, but the problem is we're going to actually have to figure out what this converges to. So we have to find the sum. So S of n is equal to A, which is negative 2 over E squared, all over 1 minus your R, which is negative 2 over E. What this is going to give us negative 2 over E squared over 1 plus 2 over E, and then this looks like a complete mess. But literally ask yourself, okay, well, I got to get an LCD for every single fraction. My LCD is the biggest denominator, which is E squared. So that means I need to multiply this by an E, this by an E, this by E squared, this by E squared, and this is going to give me negative 2 over E squared, all over E squared over E squared, plus 2E over E squared. And the good thing is, once you have the same denominator, and this is what pre-cal taught you, once you have the same denominator, you can just cancel out every single denominator, and your final answer, your sum, is going to converge to negative 2 over E squared plus 2E, and this is your sum. This is one of the harder problems. It really is. And it all starts with knowing whether or not this is a geometric series. Yes, it is because there's n as the exponent, but the fact that this one doesn't match up with this n minus 1, I have to split up and do all of this work. But if you can understand this question, then you definitely get geometric series. Now, the last problem is your divergence test. And the divergence test it should be your favorite. It should be the one that you actually do every single time. And that's because when you learn all these different lessons, some things are going to diverge from the get-go. Now, there's theorems. In a divergence test, the first statement is this: if a series E of n equals 1 to infinity of A of n converges, then that means if you would have just found the limit of the inside, it would have equaled to 0. Now, please remember that this does not say that if this equals 0, then this is going to converge. It's saying that if this happens, then I could have found the limit of the inside, and it just would have gave me 0. So then what that means also is that it's enough to show that if I just go ahead and find the limit of the inside and it doesn't give me 0, then the series diverges, which is amazing because sometimes you're going to get a number where it doesn't give you 0, it gives you an actual number, which means it diverges. Now, the theory behind that is this: if I found the limit as n approaches infinity of the inside, that means what I'm actually finding, this goes back to your first section, I'm finding what the last number is going to be. And if the last number is going to be a number, that means that the rest of the actual sequence were numbers as well. Which means if I add all the numbers in the world together, that's going to give me infinity, which means it diverges. And that's the theory behind the divergence test. That if it gives me a number and it doesn't give me 0, then if I add up all those numbers, it's going to diverge. So once again, if I find a limit as a event and it gives me 0, it does not mean, and this is the key word, does not mean that the series is going to converge. It means that I can't use the divergence test and I have to use a different test. So we're going to go ahead and do an example. So in this example, it tells us that our series from n equals 1 to infinity of this equation, we don't know what to do. This is not a geometric series. This is also not a telescoping series. So what that means is, okay, well, let's just go ahead and do the divergence test. Let's find the limit. Let's find the limit of the inside as n goes to infinity of the inside, which is 2n squared minus 5 over 3n squared minus 1. Remember all your theories of limits. Anytime you plug infinity, it's going to give you infinity over infinity. You can do the horizontal asymptote test. Since the degrees are the same, you divide the exponents, which this is going to be 2 over 3. That means that your last term, remember this is A of n, your last term is going to be 2/3. which means all the numbers before that, all the numbers were numbers as well. If you add up all numbers in the world, you're probably going to get infinity, which means that this is going to diverge. Which also means that you do not have to do anything else because this is not going to converge and there is not going to be a sum for this series. So the most important thing when you're working this out is, how do you know what you're working with? Well, the first thing that you're going to try to do is a divergence test. Because if you see that your limit of the inside does not give you 0 and it gives you a number, that means it's going to diverge. But in the case that it does give you 0, it doesn't tell you anything. It doesn't tell you if it converges or diverges. It just means you have to do a different test. If you use a telescoping series and you notice that you're adding and subtracting 2 different or 3 different fractions, you're probably going to have a telescoping series. If it's ever a geometric series, you probably know it's a geometric series because of the fact that your exponent is n. Okay? Now, you could always apply divergence test first, and if it does not give you 0, then the series diverges. This is the most important one, so please keep in mind of this. This is your longest section, reason why this video is going to 25 minutes, but if you get this section, then the rest of them will be a little bit easier, and everything else will be easier, okay? So thank you for watching, hope it helped, and good luck.